Hello students, we are discussing Unit 2 Communication and Computer Gadgets. In the previous video lecture, we have discussed about the electronic calculator and digital clock. In this video lecture, we will be discussing about the automobile computers, that is, in-car computers. Every minute of the day, someone somewhere dies in a road accident because a driver had made a human but fatal mistake. With more traffic on the road today than ever before, many traffic engineers long for the day when each car will be controlled by a computer and the driver can sit back in his seat knowing that the computer will steer him safely clearly of all potential accident and traffic jams. What are all the possibilities of in a car computer? Ideally, of course, car would be totally automatic. Information supplied by cables buried in the road would be received by the car's central computer terminal, and the car could then be automatically guided to its destination swiftly and safely. All the drivers would have to do is switch on the car and tell it where he wanted to go. Much of the basic technology for this kind of control is already existing, but for the foreseeable future, at least silicon chip microprocessor will be used to monitor and control just a few specific functions on a conventional driven car. Extended use of integrated circuits will result in electronics taking over more complex jobs in cars, commands and control system. Solid state devices contains no inherent wear out mechanisms. Because of their proven reliability, solid state devices and systems are perhaps the only practical and economical way to realize safety, environmental cleanness, and conveniency required for the state of the art automobiles. With enforcing breathing down their necks, the automakers are necessarily devoting most of their efforts to solving the problem of reducing exhaust emission and developing passive restraint devices to compile the regulation. Considerably, progress has already been made towards reducing pollution from automobiles. Possible applications of solid states in automobiles are being shown in the tabular column, which I have been presented here. With the advent of the chip and its continuous refinement, it is easy to equip a car with a small central computer powerful enough to allow complete automation of the car functions. The microprocessor for a fuel injection system, for instance, need to have information on engine speed and load setting, air temperature and air density. If it is to provide correct mixture under all conditions, and even this may not be enough. Each of these quantities requires a separate sensor, each of which must be interfaced with the computer. Whether the sensor registers as a varying electrical resistance, as a signal from a photocell or whatever, it must be translated into a form that computer can understand. Unfortunately, information from sensor is rarely in the digital language that computer operates in it. Is usually in the analog form. Converting from analog to digital form adds to the complexity and expands. Then there is the outward interface to the one that changes the computer decision into action on the car. This usually means first amplifying the output of the chip by a large degree. Then there need to be some way of changing the electrical digital signal into its mechanical analog so that the signal can, for instance, operate the car brake. This is not usually too difficult to achieve. A great difficulty is avoiding the setting up of unwanted oscillations. This is because the control system from a closed loop, the brake sends a signal to the computer. The computer sends a signal back to the brakes telling them to ease off or brake harder. So the signal that the brakes are sending alerts, and this in turn alerts the computer's output signal. If the system is designed and adjusted correctly, then the difference between what the brakes are doing and what the computer wants them to do will get progressively smaller as the information and command signal messages continues. But in some cases, the computer might overcorrect the error. The result is that the error will get progressively larger instead of smaller, and the system will go into oscillation, probably fatal if it occurs in a braking system. It is clear that the problem of interfacing are far more of an obstacle to the development of the computerized car than the computer itself. Computer systems are already well developed and their capabilities known, and it is the perplexity of the interface that are observing the majority of the research into electronic system of cars. Electronic ignition. Development of electronic fuel supply and ignition control has been given an extra boost by the introduction of strict law governing the amount of polluting gases that may be present in the exhaust. The limit can be met only by the controlled ignition timing and fuel delivery far more accurately than had previously been the case. Many cars now have electronic ignition, although most are still timed mechanically. A number of more recent systems have begun to incorporate microprocessor to improve the accuracy with which the ignition is timed to fire the spark plug. Data is supplied to the microprocessor concerning engine speed, the position of the piston, and the load of the engine. The microprocessor then compares the information it receives with instruction imprinted in its memory during manufacturing, and the ignition is duly fired at the correct moment. This sort of facility had already been shown to improve the performance and reduce toxic emission. These systems, however, are only a starting point, and the potential for processor control is much greater. For instance, by the end of 1970s, a number of manufacturers had introduced a knock sensor. This is valuable because engine could be more efficient if they run on higher compression ratio. At present, petrol engines rarely have compression ratio of more than 10 to 1, and restriction on the lead content in petrol often make them much lower. If they were any higher, the engine could be subject to denote or knocking. When this occurs, some of the mixture explodes violently before it is ignited rather than simply burning. Knocking not only wastes power but can work the engine. The knock sensor detects knocking as it about to start. Since inspecting knocking shows up an unusual variation in crankshaft speed before audible knocking begins. If knocking is detected, the processor retards the injection to prevent it. Fuel injection systems have been using microprocessor for some years, originally varying the mixture only according to the engine speed and throttle setting. Many systems now include sensors for monitoring such things as engine temperature, air pressure, and so on. More recently, the German manufacturer Bosch introduced a lambda sensor to detect the amount of oxygen in the exhaust. It works by checking the electrical conductivity of the exhaust gas. Any deviation from the set limit can then be corrected by altering the fuel injection section via the microprocessor. Electronic operation of engine valves open up a further an enormous range of possibilities. It would, for instance, allow the driver to change the characteristics of an engine at will. At the flicking of a switch, he could change the car from a highly turned point to a economically slugger with the plenty of pulling power simply by altering the timing and duration of valve opening. Or he could shut off the valve altogether, turning the engine into an air compressor for an efficient engine braking. In electronic ignition lock system, to prevent drunken driving, the basic idea is to flash an arbitrary sequence of letters on a screen very briefly and then require the driver to push a set of buttons in the same order. Tests have shown that better discrimination between drivers who are drunk and those who simply have poor retention of visual image is obtained by requiring the task to be performed in several short sequences rather than one long sequence. On this basis, the following sequences proposed. There will be 4 buttons labeled A, B, C and D. 3 legal sequences are listed in the figure as shown here. When the system is turned on, sequence 1 will be displayed, after which the driver must punch the button in that order. If the driver is successful, sequence 2 will be displayed, and if it is successfully repeated, sequence 3 will be displayed. Only if all the sequences are correctly followed will the ignition be turned on. If the driver makes a mistake at any point, the keyboard will be mechanically locked to prevent further operation and may be released only by removing the ignition key and starting over. The basic block diagram of the system is shown in this figure. The counter contains the number of sequences being used, always starting with 1 when turned on. The sequence detector checks the sequence. If an error is made in a sequence, the error signal E is used to disable the system. If the sequence is correctly completed, a pulse is used on one of the line P1 or P2 or P3 corresponding to the sequence 1, 2 or 3 respectively. The information is compared by comparator with the number of sequences that was displayed. If they agree for sequence 1 or 2, the counter is stepped to the next number to start the next sequence. After agreement on sequence 3, the ignition is turned on. If the pulse received by the comparator does not match the content of the counter, a disabling error signal is issued by the comparator. The keyboard is so constructed that each button may be pushed only once for a given sequence. A one level will be supplied to the comparator by the keyboard on a line labeled complete after the 4th button has been depressed. The comparator will ignore any pulse input occurring before complete is equal to 1. Anti-lock braking system, ABS. The ABS is an advanced braking system which comes into play when there is a panic brake situation. The braking action with and without ABS is shown in the figure. In case 1, when a part of car without ABS is on a slippery surface and the brake is applied, the car swirls. The car with ABS stays on course. In case 2, while taking a curve, the car without ABS goes off course while the one with ABS stays on course. In traditional braking system, the braking effect on all the wheel is equal when the brake pedal is depressed. The braking effect on rear wheel is more than on front wheel is subsequently developed. In this case, when brakes are applied in a panic situation, the rear wheel gets locked and the wheel skids. This effectively increases the braking distance. ABS reduces the skid effect and helps the vehicle to stay on course. The heart of ABS is the microprocessor based unit which senses the wheel speed and modulates the braking on the wheel. The system takes over the braking action only during sudden braking. Electronic controlled suspension. The Mitsubishi system with the acronym ECS has been designed to keep the car flat and level when riding over bumps accelerating and cornering. It achieves this with damper valve that can be independently addressed by the car's suspension computer to vary their damping effect, additional air springs for load sharing, and also to alter the height of the car. The process has sensors which detect steering angle, gravity, road speed, the height of the vehicle at the front and rear, the accelerator position, and the rate of movement of various suspension components. While there is some degree of drive override, the sensor gradually controls the pump of the air, spring and damper valve. When concerned, for example, two sets of sensors are used. Either the steering angle and the vehicle speed input determine the process instruction to the air spring and damper valves, or a triaxial G-force accelerator information the process of lateral acceleration so that changes can be made. Noise dive under braking is not only uncomfortable, it is dangerous. In an accident, a car which has noise dived severely is likely to go underneath the car in front, and the impact would be taken by the car's windscreen. By monitoring vehicle speed, longitudinal G-force and brake pedal application, the processor knows that the car is braking and not just going on hill. It adjusts the ride height of the front of the car to maintain a level ride. Similar input are analyzed when the car is being sharply accelerated, except that the override factor is throttle position, not brake application. In this case, adjustments are made to the car rear suspension until to keep the backup. As a front wheel drive car dips at the rear, the front wheel changes their angle of contact with the road. If this changes too quickly, the front driving wheel can lose traction. The sensors which monitor rear suspension also check on the load the car is carrying and keep the rear up. One of the most uncomfortable side effects of soft riding suspension system is pitch and bounce. The car either bounces vertically over sympathetic bump or pitches back and forth over bumps which are asynchronous with the car suspension. By monitoring front rear suspension, high relationship and suspension travel, the process can instruct the offending wheel damper value to change characteristics and eliminate the unwanted movements. Instrument panel displays. Instrument panel displays in the form of instrument cluster act as information source for the drivers. Instrument clusters usually display parameters like speed, RPM, fuel level, temperature, distance traveled, and trip meter, and various alarms as individual displays. Modern cars have few features like trip computers which are able to offer information like average speed, average fuel consumption, mileage per liter, time, and other features. Newer car versions incorporate instrument clusters with microprocessors which can perform advanced functions. The processor carries out the entire signal processing. Conventional needle-based display have been largely retained. Accordingly, familiarity and conveniency to the old school car users. Stepper motors are used to rotate the needle in these meters, but some bold modern car manufacturers have stepped out of this line of thinking and replaced the displays partially or completely with liquid crystal display based digital display depending on the function being incorporated. Most of the processor based designs uses application specific standard process ASSP, that is application specific standard process, or system on chip SoC. In this application specific standard process, all peripherals like digital and analog input outputs, LCD and stepper motor drivers, lamp drivers, etc. are integrated with the CPU core as a single IC. This is not only reduce the cost but also enhances the reliability. Electronically erasable programmable ROMs are used to store information like the odometer data and other parameters for compensation of the temperature, fuel tank dimension, etc. This data is normally encrypted for security purpose. As an example of a dashboard computer of motor vehicle is shown in the figure. Trip computer used in present day cars are incorporated as separate units or integrated as part of the vehicle instrument cluster on the dashboard. These trip computers provide details like estimation of distance that can be traveled with the remaining fuel instantaneously and average fuel economic amount of fuel used, average speed, estimated time of arrival, oil diagnostic indication, etc. Ultrasonic car safety belt system. One of the results of car safety belt system developed by Mullard and the Ford Motor means that the car thief will have to strap himself if he wishes to make off with his booty. The belt must not only be fastened but also positioned correctly across the wearer, as shown in the figure. The block diagram in the figure shows before the ignition will function, the driver must occupy his seat activating a pressure switch beneath it, buckling the belt across his lap and close the belt switch. Provided the belt is wound correctly, a 40 kHz signal emitted from an ultrasonic transmitter mounted in the belt is received by a detector built in the windscreen pillar, which in turn completes the ignition circuit. In the front passenger seat is occupied, then a 50 kHz signal must be received from the passenger's safety belt before the ignition switch will be functional. If the correct sequence has not been carried out, a logic circuit will trigger an audible and visible alarm mounted on the dashboard. The system can be arranged so that if the belt is unfastened while the car is moving, the ignition is not immediately affected. Instead, the alarm is sounded, and if at the end of the specified time the belt still remains unfastened, the ignition will then be cut off. For every short operation, such as parking or garging the car, the logical arrangement can be adjusted to allow for car movement in first or reverse gear for a specified time without the driver being belted. Airbag system. The system prevents the driver and front seat passenger from crashing against the steering wheel and into the windshield. This is achieved by physical intervention of an airbag placed in the steering wheel and in the front deck, which pops up and inflates instantly to provide an air cushion. The system consists of two portions, the crash sensor and inflammation mechanism. Crash sensor or acceleration sensors are mainly used to achieve airbag release in the event of crash. In the event of a crash, these sensors detect the impact and inflate an airbag which is in the steering wheel for the driver and in the dashboard of the co-driver. These sensors are either mechanical or electrical. The mechanical sensors are for switching type. The electrical sensors are based on piezoelectric crystal. These sensors are extremely sensitive and are also used to measure impact. Fitted in the front of the car, this sensor closes the contact, which in turn triggers the inflation mechanism. The inflation mechanism is a chemical reaction that generates inert gas to inflate the airbag. Vehicle proximity reduction system. Over 500,000 automobile accidents each year results from improper overtaking. The frightening statistics might be reduced substantially if a near solid state detection system developed by Selvian's Wakefield Development Laboratories were to come into widespread use. It is designed to meet the specification of a major automobile manufacturer Selvian's vehicle proximity detection system model HS200 will respond to vehicle with 30 feet of its sensor covering an area slightly larger than a single traffic lane. Its intent application is to alert a driver to vehicles moving into his rear blind zone as shown in the figure. A passive ultrasonic system, the HS200, reacts only to those high frequency sounds generated by a moving vehicle, such as road and engine noise. A passive design approach was selected by Sylvian's engineers when it was found that simple active system as general could not discriminate between real target vehicle and such stationary object as fences, signposts, tunnels, etc. and moreover were extremely sensitive to rain, snow, dust, salt, shock, vibration and severe temperature changes. The system functional block diagram is shown here. In operation, signal picked up by an ultrasonic transducer, that is microphone, equipped with a directional horn or coupled through a tuned circuit to a high gain solid state amplifier. An automatic gain control AGC circuit with a 20 decibels dynamic range serves to suppress ambient highway noises, while a signal integrator and threshold detector together ensures a response only to target vehicles, rejecting shock and simpler pulses like signals. The signal is cleaned up and fed to a solid state lamp driver. The output is a 10 volts 100 milliamps DC signal capable of energizing a panel lamp on the vehicle's dash. Circuit parameters are chosen so that the system is intensive to vehicle traveling at least 35 miles per hour, thus avoiding nuisance alarms when in bumper to bumper city traffic. In practice, the pickup transducers may be mounted either in a special rear view mirror package or within the vehicle feeder as part of a tail and turn light assembly. The electronic control module may be placed whenever convenient. Car navigation system. The navigation system indicates the location and running direction at the center of its CRT display. As the vehicle moves, one after another map is sent to the display automatically. The system is composed of GPS receiver, earth magnetic sensor, speed sensor, horizontal antenna 13 cm in diameter and control unit, a CD-ROM driver unit and 6-inch CRT. About 500 maps of one of 25,000 scale may be stored in one compact disc. Apart from measuring the location by means of radio waves from a satellite, this system is also equipped to determine location by means of earth magnetism and the speed of the vehicle. Therefore, it is capable of indicating the location of vehicle even with a tunnel or between tall buildings. So that's all with today's video. See you all in the next video. Thank you.